Have you ever heard of a country digging straight into the heart of a mountain, not to extract gold, coal, or some rare mineral, but to build a massive underground tank of water designed to listen to the tiniest whispers of the universe? It might sound like a science fiction plot or the backdrop of some futuristic secret facility, but what's happening right now, deep inside a remote mountain in Japan, is very real, and it just might reshape how we understand reality itself. This isn't just another construction project. It's a $600 million, decades in the making, globally coordinated scientific effort hidden from view beneath layers of stone. So, what exactly is Japan building inside this mountain? Why is it taking so long? And why are the world's brightest scientists so obsessed with something that's virtually invisible to the human eye? Something enormous is taking shape in the Japanese Alps, a region known for its pristine natural beauty and peaceful remoteness. But under the ground, far away from curious eyes and shielded by nearly 700 meters of solid rock, Japan is constructing the largest neutrino observatory in the world. When it's done, the facility will be over 80 meters tall and nearly 70 meters wide, enormous enough to house a Boeing 747 jet standing on its tail. Despite its scale, most people will never even see it because this entire structure is being hollowed out from inside a mountain. The project is called Hyper Kamiokande, and it's not just the biggest of its kind. It's one of the most ambitious experiments in modern physics. Behind its towering size and complex construction lies a simple but profound question. What are neutrinos, and what can they teach us about the nature of the universe? Let's rewind and understand what this all means. Our universe, as modern physics explains, is built from unimaginably tiny subatomic particles, things like quarks, electrons, photons, and bosons. Among these is a particularly elusive one, the neutrino. Neutrinos are the lightest and most ghostly of all known particles. They barely interact with anything, flying through matter, planets, and even you right now, trillions of them every second, without leaving a trace. You might be surrounded by them at this very moment, but you would never know it. And that's precisely what makes them so fascinating and so important to study. Understanding neutrinos could unlock answers to questions that have stumped scientists for decades. Questions about why the universe is the way it is, and whether the laws of physics as we know them are complete. But here's the catch. Because neutrinos are so hard to detect, scientists need very special environments to even have a chance at spotting them. You can't just go out with a telescope or a microscope and expect to find them. One common approach involves smashing atoms together at near light speed and observing the resulting chaos, like what's done at CERN's Large Hadron Collider. But there's another way, a quieter, more passive method. You listen for them. And that requires an incredibly silent, stable, and isolated environment, completely free from other types of interference. In short, you need a mountain, preferably a very remote one, and Japan has just the place. Enter Mount Nugo in Kamioka, a small town nestled in the Japanese Alps. This quiet, peaceful region is the perfect setting for one of the most complex scientific experiments in human history. Here, more than 680 meters below the mountain's peak, the Hyper Kamiokande facility is being painstakingly carved from solid rock. But this isn't Japan's first dance with neutrino science. Back in 1983, the first version of this experiment, known simply as Kamiokande, was built with the help of a local zinc mining company. That initial setup proved to be a major breakthrough and showed the world that neutrino detection was possible. Building on that success, a second, larger observatory called Super Kamiokande was completed in 1996. Now, nearly 3 decades later, Hyper Kamiokande represents the third, and by far the most ambitious, evolution of this journey. So how exactly do you go about constructing something like this inside a mountain? The logistics alone are mind-blowing. Planning for the Hyper Kamiokande began way back in 1999. That's more than 20 years of designs, discussions, feasibility studies, and technological development before any actual construction began. When ground was finally broken in May 2021, the first task was to create an access tunnel. Using a technique known as drill and blast, engineers excavated a 2-kilometer-long approach tunnel in just 9 months. A remarkable feat, considering the scale and complexity of the terrain. Once that was complete, they sprayed the entire tunnel with concrete to stabilize the structure and prepare it for daily use by workers and scientists. That access tunnel leads to what will become the roof of the observatory. Because the entire chamber will be located deep inside the mountain, 681 meters below the summit, the roof had to be specially reinforced. Engineers constructed a dome-like structure at the top of the cavern, then supported it with a massive steel truss designed to bear the incredible weight of the rock above. That portion of the project was finished in October 2023, and now the focus has shifted to blasting downward an additional 71 meters through bedrock to create the vast interior chamber where the experiments will be conducted. Just to give you an idea, the amount of rock being excavated is enough to bury several city blocks. But it's not just about size. The location and geology of Mount Nugo were chosen for a very specific reason. The dense rock that surrounds the observatory provides an ideal natural shield against cosmic rays and other background radiation that would otherwise interfere with the sensitive measurements. In scientific terms, the shielding effect is equivalent to placing the observatory 1.7 kilometers under the ocean. That's how well protected it will be from external noise. For neutrinos, though, it's no obstacle. These tiny particles can fly through whole planets without missing a beat, so this level of shielding does nothing to stop them. But it does prevent almost everything else from getting in the way. That's what makes this location so perfect for the work ahead. The excavation phase is expected to wrap up in 2025, but even when that's done, the facility won't be ready to detect a single particle. That's just the beginning of what comes next. The interior of the massive cavern will be lined with not one, but 2 layers of concrete for durability and stability. Between those layers, a highly advanced waterproof membrane will be installed to ensure that the chamber is completely sealed. And that's because what comes next is even more incredible. The chamber will be transformed into the largest tank of pure water on the planet. Once the massive cavern inside Mount Nugo is fully excavated, lined, and sealed, it will be transformed into the largest water tank ever constructed on Earth. This isn't an exaggeration. It will hold 260 million liters of water, enough to fill more than 100 Olympic-sized swimming pools, and over 4.5 times the capacity of the world's largest public aquarium, located at SeaWorld Abu Dhabi. The process of filling this massive underground tank will take about 6 months, drawing water gradually from the natural water table deep within the mountain itself. But it's not just any water that's needed here. The experiment demands water so pure that it reaches a level of chemical cleanliness that is almost otherworldly. After it's pumped in, the water will go through several advanced purification stages, including UV light treatment and specialized filtering systems, to strip it of any contaminants or particles. By the end of the process, the water will be so pure that it can literally dissolve metal over time due to its aggressive chemical properties in a state of ultra-purity. But why all this water? What role does it play in observing something as small and intangible as a neutrino? The answer lies in a fascinating phenomenon known as Cherenkov radiation. When a neutrino, by some rare chance, collides with an electron inside this vast volume of water, it causes a very faint blue glow to be emitted. This is Cherenkov radiation. It's similar to the visual effect you might see when a particle moves faster than light does through a medium like water. And yes, that's possible because light travels slower in water than it does in a vacuum. This subtle blue flash is exactly what scientists are looking for. It's the calling card of a neutrino interaction. But detecting that flash, in a space this large and this dark, is like looking for a single candle flicker in a cavern the size of a cathedral. To accomplish that, the Hyper Kamiokande will rely on a vast array of highly sensitive photodetectors. These are specialized light sensors that can register even the faintest photons of light with exceptional precision. When the chamber is operational, it will be lined with 40,000 of these photodetectors, each one custom designed and nearly twice as sensitive as those used in its predecessor, the Super Kamiokande. These detectors work together to act as a giant camera, capturing and reconstructing the tiny glimmers of light emitted during neutrino interactions. Their sensitivity is so extreme that just one of these sensors, in complete darkness, could detect the light of a flashlight on the surface of the moon. That's not metaphor or exaggeration. It's the level of precision these devices actually offer. To ensure their performance, these new generation sensors are also being specially reinforced to withstand the pressure of 260,000 tons of water. That kind of water weight creates immense forces on the detector casings, so the structural engineering behind them is just as advanced as the electronics inside. Every component is carefully tested for both pressure resistance and electrical sensitivity before installation, and because there are tens of thousands of them, manufacturing and testing them is a massive industrial task in itself, involving multiple international partners and laboratories from around the world. To understand how this will look when it's all finished, we can take a close look at the Hyper Kamiokandé's predecessor, the Super Kamiokande. Though only about half the size, it shares the same underlying design and principle. At Super Kamiokande, the cylindrical chamber is currently drained of water to allow maintenance crews to access the photodetectors. When viewed without the water, the chamber looks like something out of science fiction, a metallic gold cavern, ringed by thousands of identical sensors, stretching from floor to ceiling. It's like staring into a massive mechanical eye. Each sensor is positioned with mathematical precision, designed to capture data that can then be reconstructed by computers into a visual map of particle interactions. Once Hyper Kamiokande is completed and operational, it will be able to collect even more detailed data from even rarer neutrino events, thanks to its increased size, more advanced sensor technology, and greater depth within the mountain. But this observatory isn't just for neutrino detection. It's also a platform for a wide range of other experiments in particle physics, many of which are designed to explore why the universe exists in its current form. One of the big mysteries the project aims to help solve is called matter-antimatter asymmetry. In simple terms, physicists believe that when the universe was born from the Big Bang, it should have produced equal amounts of matter and antimatter. Yet somehow matter won out, and antimatter almost completely vanished. Neutrinos might be the key to understanding why that happened. By analyzing how neutrinos behave, especially how they change types or oscillate between different states, scientists can learn more about this cosmic imbalance and potentially uncover new laws of physics. Hyper Kamiokande is also likely to be one of the first places on Earth to detect neutrinos from supernovae, when a massive star collapses and explodes in a distant galaxy. These kinds of cosmic events release a flood of neutrinos before they emit light, which means Hyper Kamiokande could act as an early warning system for astronomers around the world. If a supernova were to occur nearby in our galaxy, the observatory could pick up the neutrino signals hours before we see it with telescopes, giving humanity a first glimpse into the death throes of a star before the light even reaches us. Beyond space and astrophysics, the technology behind this observatory could also impact everyday life. The sensors developed for this project are pushing the boundaries of light detection technology. In the long run, improvements made here could translate into better medical imaging, more precise radiation treatments, and faster, more accurate environmental sensors. In fact, if you've ever had a PET scan or CT scan, you're already benefiting from the kind of physics research that comes from facilities like this. It's easy to assume particle physics is all theory and no practical value, but history shows that many of today's technologies, including medical diagnostics, GPS timing systems, and even the World Wide Web, originated from labs and experiments that were once considered purely theoretical. The collaboration driving Hyper Kamiokande is also worth noting. While Japan is leading the construction through the University of Tokyo, the project brings together scientists from 21 countries, representing a truly global effort. From data analysis to component manufacturing to theoretical modeling and software development, every part of the planet has a hand in this. This kind of global scientific partnership is a reminder that while politics and borders often divide us, science has a way of bringing people together around a shared curiosity about the universe. As of now, the excavation of the Hyper Kamiokande chamber is scheduled to complete in 2025. After that, the installation of the waterproof lining, the purification system, and the photo detectors will begin. Full construction is expected to wrap up in 2026, and by 2027, if all goes according to plan, the Hyper Kamiokande will be operational, ready to detect its first neutrinos and perhaps even answer questions we haven't yet thought to ask. This is not just a monument to human engineering or to Japanese ingenuity, though it is clearly both. It's a monument to curiosity, the same force that has driven humanity from the caves to the stars, from telescopes to particle accelerators, from myths to mathematics. And it's all happening quietly, in the heart of a mountain that most of us will never see. So why go to all this trouble for something that is nearly invisible? Why build a structure the size of a skyscraper, fill it with ultra-pure water, bury it inside a mountain, and wait patiently for particles that might never even touch anything? The answer comes down to one of the most profound quests of modern science: to understand the universe at its most fundamental level. You see, neutrinos are not just tiny particles. They are keys to unlocking the deepest mysteries of existence. Their ghost-like nature makes them almost impossible to study, but that same nature also means they carry information from places and moments that no other particle can reach. They are born in the hearts of stars, in the explosions of supernovae, in the radioactive decay of elements on Earth, and even from processes that occur just seconds after the Big Bang itself. In a way, every neutrino is a message from the most extreme corners of space and time, and Japan's massive underground observatory is designed to catch them. When Hyper Kamiokande comes online, it won't just be a passive sensor. It will be part of a larger experimental framework that includes sending artificial beams of neutrinos directly through the Earth. One of the most ambitious collaborations associated with this project is the Tokai to Kamioka T2K experiment. In this setup, a powerful particle accelerator on Japan's east coast, in Tokai, will shoot a beam of neutrinos more than 295 kilometers directly through the Earth's crust to the Hyper Kamiokande detector. Because neutrinos can travel through matter without being stopped, the beam doesn't need a tunnel. It just goes straight through rock, mountains, rivers, and everything in between. Scientists can then analyze how the neutrinos have changed along the way, allowing them to study the phenomena of neutrino oscillation, a process where one type of neutrino transforms into another as it travels. This could help explain not just the nature of neutrinos, but potentially why there's more matter than antimatter in the universe. That one insight could rewrite the story of creation as we know it. And it's not just physics textbooks that will change. The real-world implications of what Hyper Kamiokande might uncover are impossible to fully predict. But the history of science tells us to expect the unexpected. Particle physics has a strange way of shaping our world. For example, the invention of the transistor, which led to all modern electronics, came from quantum physics. The Internet began as a data-sharing tool between particle physicists. Magnetic resonance imaging, MRI, and positron emission tomography, PET scans, came from our understanding of subatomic particles. Even the Global Positioning System, GPS, relies on corrections from Einstein's theory of relativity, a framework developed to understand the behavior of fast-moving particles like electrons. So when you invest in fundamental science, you're not just chasing knowledge. You're planting seeds that often grow into world-changing technologies. And the impact isn't limited to the lab. Projects like Hyper Kamiokande create a ripple effect through education, engineering, and global collaboration. The young scientists and engineers who cut their teeth on this observatory will go on to work in industries ranging from climate science to space exploration to cybersecurity. The technology developed for monitoring sensors, water purification, and structural stability in such extreme environments often gets adopted in unexpected ways. Even the logistics and software systems built to handle the observatory's enormous data output, petabytes of raw information, are pushing forward innovations in machine learning and data infrastructure, which can then be used in fields like financial forecasting, medical diagnostics, and even autonomous vehicles. There's also something beautifully human about the entire endeavor. It represents a massive international commitment to knowledge, peace, and cooperation. In a world often divided by politics and conflict, here is a project that unites researchers from Asia, Europe, North America, and beyond, all driven by a shared desire to understand our universe just a little better. The engineers drilling through mountains, the physicists analyzing oscillation data, the technicians polishing sensitive lenses, all of them are participating in something much bigger than themselves. Hyper Kamiokande isn't just a structure, it's a statement, a monument to the idea that knowledge is worth pursuing, even if it takes decades to get there. There's also a deeper philosophical question at the heart of all this. Why are we here? Not just in Japan or on Earth, but in the universe at all. Why does anything exist rather than nothing? Science may never fully answer these questions, but neutrinos and the experiments designed to study them may bring us closer than we've ever been. For decades, neutrinos have defied our models, stubbornly refusing to behave exactly as expected. They are neutral, nearly massless, and barely interact with anything. But they are also abundant. Trillions pass through your body every second, unnoticed. If we can understand them, we can perhaps understand how the universe evolved from a sea of energy into a place filled with stars, galaxies, planets, and life. So, yes, Japan is hollowing out a mountain, but not to mine gold or build weapons or make profit. They're doing it to build one of the most sensitive instruments ever created by humans, one that listens for whispers from the beginning of time. They're creating an artificial silence in the heart of a mountain so that they can hear the universe speak. And that, if nothing else, should fill us with awe. When you watch this structure slowly take form, first the access tunnel, then the dome, then the blast walls and sensor arrays, it's hard not to feel like you're witnessing the construction of a temple. Not a temple to gods, but a temple to curiosity. A cathedral of science buried deep in the earth, where lightless particles are caught in flashes of blue, and where the laws of reality itself may one day be rewritten. And when it finally begins operation in 2027, the Hyper Kamiokande will become the most advanced tool in the world for detecting and understanding neutrinos. But more than that, it will be a beacon, a reminder that humanity is still asking questions, still dreaming, still digging deep, literally and metaphorically, in search of meaning. Not because we have to, but because we can. So the next time you hear about a mountain in Japan being hollowed out, remember, it's not just an engineering marvel or a scientific experiment. It's a symbol of who we are as a species. We wonder, we question, we build, we explore, and sometimes we carve into the very bones of the earth itself just to understand what lies beyond the stars. That's why Japan is hollowing out a mountain.